All right, here is problem 111, page 469. This is the last of the problems on homework set 32 that we're going to video. You have a sister problem, 112, and this is an application problem and it involves projectile motion. So you've seen projectile motion in the past, and if you take physics here at COS, or lower division physics anywhere, you're going to find that when you start that, you're going to be dealing with a subject called mechanics, and within mechanics, a subject called dynamics, which involves particles, which are mathematical constructs, zero dimensions, but they carry mass. Particles under the influence of Newton's laws. How do they behave? How do they move? And you're going to find that the equations of motions are quadratic in nature. But if you start to extend that motion to two dimensions, x and y, you're going to deduce angles, and you're thereby going to introduce some trigonometry. So this problem, this problem has two questions A and B, so I'm actually going to do two videos, part A and part B. We're going to call this part A then. There, it's part A. And what it says is the horizontal distance that a projectile will travel in air ignoring air resistance is given by r of theta is equal to v sub o squared sine 2 theta all over g. So let's just make sure everyone knows what those are. A particle is being launched or thrown with an initial speed at an initial direction. So this is I would prefer to call this the angle of inclination. Maybe you want to call it elevation. It's the angle with respect to the horizontal. And this is the acceleration due to gravity. It's a constant acceleration due gravity. And on Earth, that's 9.8 meters per second squared. I know meters per second squared is odd, but let me take physics to understand that. Let's just accept it here, stipulate it to be true in this math class. So let me just draw a diagram for those visual learners amongst you. Here's a little guy. He's got his arm cocked back. He's striding forward. And boy, that looks silly. But he's got a ball. Look out, he's got a ball. And he is throwing it at some angle with respect to the horizontal. Yeah, some angle with respect to the horizontal and at some speed. And guess what? That ball is taking off in a parabolic path, and it's going to crash back to Earth someplace. And the relationship between the angle at which he throws it, the speed at which he throws it, and the distance it travels is given by r of theta. Okay? Clear enough. So let's go look at problem A. Problem A says, if you can throw a baseball at an initial speed of 34.8 meters per second, which sounds fast, by the way, at what angle of elevation theta should you direct the throw so that the ball travels a distance of 107 meters? 107 meters. Holy Toledo. Okay, wait, let 34.8 meters let be equal to V0 and r of theta be equal to 107 meters. And I got to tell you, that's a pretty darn good throw. Let me just waste your time for a second. What is 34.4 meters? What is 34.8 meters per second? That's like 1.1 more yards. That's like that many feet per second. So 88 feet per second is 60 miles an hour. Well, okay, it won't get you into the big leagues, but it's 78 miles per hour. You throw that in the big leagues and everybody hits you. But it's quite a speed to get, and 107 is a pretty good toss to be made. Can be made, not by me, but I've known people who could do it. I think I couldn't name you one right now. So let me just shut up and let's do this. Let's go ahead and insert these into this, and you will find that we'll end up with with an equation for theta, and we'll be able to calculate theta, presumably. So r of theta is 107 meters. It's equal to v sub o squared, 34.8 squared meters squared seconds squared, right? Times 1 over g, which is 9.8 meters per second squared, times 2 sine of 2 theta. So let's just quickly check the units here. I hear that's what physicists do. Here's a second squared, they cancel. Here's a meter and a meter squared, leaving meters on this side, meters over there. I think we're doing everything right. So let's just calculate what the sine of 2 theta is. Then let me write it down, and then we can check and see if it's right. It's 107 divided by 34.8 squared times 9.8. We know the units are right, so we're just going to let them fly. And I'm going to calculate this, 107, 34.8, square that and divide it, and 9.8 times. And I'm going to get a number, and that number is 0.865 ... So if I take the arc sine of both sides of this, sine 2 theta is equal to this, I'm going to get 2 theta is equal to some number, divide by 2, and I'm going to get theta. But hold on just a second. Let's do this. Let's go look at, not sine of 2 theta, let me draw r of theta here versus 2 theta, right? What's going to happen here? R of theta is a constant times the sine of 2 theta. So it goes like this, right? Goes like that. And I don't think we care about this part where r of theta is negative. That, you know, what that is a physical part. That's how r of theta increases if you allow, well, actually I don't know about that. R of theta, no, it's not that. It's what happens when you start to throw the ball backwards, right? This is, what is this? This is pi, of course. Should be pi. So when theta equals 0 to when theta goes from 0 to pi over 2, you're throwing the ball forwards. Past theta equals pi over 2, or 2 theta equals pi, you're throwing the ball this way. So we don't care about that. But what we do note here is that I might have 2 solutions. In fact, now, if I make another picture, only this time I draw sine of 2 theta versus 2 theta. Here it goes, same thing, right? But looky there. What is this number right here? This is pi. I want to say this is theta equals pi over 2, and that's maybe what I should have done. Theta equals pi over 2. So looky there. If this is 0.865, there are 2 angles between 0 and pi over 2 for which sine of 2 theta is equal to this value, right? Here's one of them right there. There's one of them right there. All I have to do now is take the arc sine of this value. I'm making sure my calculator is in radian mode. I just did it. I'm going to divide by 2, and I'm going to get 0.52 radians. 0.52 radians. And 0.52 radians is about 30 degrees, right? Let me just do this in degrees. In fact, I'm going to see how close it is to 30 degrees, because what do? I have to multiply that by 180, and then I have to divide it by pi. And yeah, pretty darn close to 30 degrees. And if that's 30 degrees, this is 30 degrees less 90 degrees. This is 60 degrees. So kind of a cute problem. That says there's 2 ways to throw at 107. I'm sorry, now I put that drawing up at the top there. Let me make a little smaller version of this drawing real quick and then move on. Here's our guy throwing the ball. Here's how far he's thrown it, and he can throw it under 7 by throwing it at 30 degrees. There's your 107. Or he can lob it up to 60 degrees. There's your 60 degrees. And there's your two answers. And that's the end of part A. Come on back and let's see part B.